Hello everyone. In this video, I'll discuss a key topic commonly asked in interviews. What are clock skew and clock jitter, and how do they impact setup and hold timing constraints? So let's get started. Ideally, the clock edge should arrive at the same time for all the flip-flops in the design. However, due to non-idealities in the clock distribution network, the clock edge may reach different flip-flops at different times. There are two primary types of non-idealities that must be considered during circuit design: clock skew and clock jitter. In a digital design, due to the differences in the interconnect wire lengths and variations in the wire parasitics, the same clock edge may arrive at different flip-flops at different times. The difference in the arrival times of the same clock edge at two related flip-flops is called clock skew. In the figure shown over here, we have two flip-flops, launch flop FF0 and capture flop FF1. Due to the variations in the clock interconnect paths, there is a skew between the same clock edges arriving at launch flop and the capture flop. This skew is illustrated in the diagram as the gray shaded area. Let's denote it by T skew. Now let's understand how clock skew impacts setup and hold constraints. First, the setup constraint. The setup constraint equation, assuming that there is no skew in the design, is given as T must be greater than T clock to Q plus T PD logic plus T setup. In this equation, T is clock period, T clock to Q is the clock to Q delay of the launch flop, TPD logic is the propagation delay through the combinational logic, and T setup is the setup time of the capture flop. If we include clock skew in the setup timing constraint, it is given as T plus T skew must be greater than T clock to Q plus TPD logic plus T setup. Now let's understand how positive or negative clock skew impact the setup constraint. When the clock skew is positive, it effectively provides more time for the data to travel from launch flop to the capture flop, making it easier to meet setup requirements. This also helps push the operating frequency of the design higher. On the contrary, negative skew reduces the time available for the data to propagate, making it harder to meet the setup requirement. Now let's look at hold time constraint. Assuming there is no skew in the design, the hold time constraint is given as TCD register plus TCD logic must be greater than T hold. In this case, T hold is the hold time of the capture flop. TCD register and TCD logic are the contamination delays of the launch flop and the combinational logic block respectively. If we include clock skew in this equation, it is written as T hold plus T skew must be less than T contamination delay of register plus T contamination delay of logic. For the hold time constraint, a positive clock skew is undesirable. In this case, the data at the input of the capture flop must remain stable for a much longer time after the clock edge to ensure it is captured correctly. This increases the risk of hold time violations. On the contrary, negative clock skew can be beneficial for satisfying hold time constraint as it effectively reduces the time for the data to be held stable, making it easier to meet the requirement. Now let's talk about clock jitter. Clock jitter refers to the random variations in the arrival times of the clock edges at different flip-flops in their design relative to the ideal reference clock. It's essentially the fluctuations in the clock period, causing rising and falling edges to appear at slightly different times than their ideal positions in the reference clock. These variations are caused by noise, power supply fluctuations, and other sources of instability in clock generation and distribution network. Now let's study the effect of clock jitter on setup and hold constraint. For the setup constraint, the worst case scenario occurs when the launch clock edge is delayed or it is arriving late and the capture clock edge arrives early. In this situation, the effective clock period is reduced to T minus 2 times of jitter, leaving less time for the data to propagate from launch flop to the capture flop. This makes it more difficult to meet the setup time requirement. In the figure shown over here, the green waveform represents the launch clock and the red waveform represents the capture clock. The nominal clock period is T. As seen, the launch clock edge is delayed, it is shifted to right, and when the capture clock is early, shown here shifted to left, this combined effect reduces the available time for the data to travel and settle at the capture flop. Here is the updated setup timing constraint equation including jitter. It's t minus 2 times of t jitter must be greater than t clock to queue plus tpd logic plus t setup. Now let's talk about hold time constraint. For the hold time constraint, the worst case scenario occurs when due to jitter, the launch clock edge arrives early and the capture clock edge arrives late. In this case, the data at the input of the capture flop must be held stable for a longer duration after the launch edge to ensure correct capture. This makes it more difficult to meet hold time requirement. In the figure shown here, when the launch clock edge is early or it is shifted to left and the capture clock edge is late or shifted to right, due to the combined effect of jitter, the data at the input of the capture flop must remain stable for additional 2 times t jitter to avoid hold violations. This is the updated hold time equation including jitter, where the contamination delay of register plus contamination delay of logic must be greater than t hold plus 2 times of jitter. If we put clock skew and clock jitter together in the setup and hold constraints, they can be written as time period t plus clock skew minus 2 times of jitter must be greater than clock to queue delay plus propagation logic delay plus t setup. Similarly, for hold constraint, the contamination delay of the register and the contamination delay of logic must be greater than hold time plus clock skew plus 2 times of jitter. Looking at these equations, it is clear that to reliably meet setup and hold timing constraints, clock skew and clock jitter must be minimized in the design. To minimize clock skew, CAD tools are used to design clock distribution trees that balance and match delays across all related flip-flops. These trees are carefully optimized to ensure that the clock signal arrives at each flip-flop as simultaneously as possible. To minimize clock jitter, phase lock loop and delay lock loops are commonly used. These circuits help stabilize the clock signal and reduce timing variations caused by noise, power supply fluctuations, or temperature changes. This is all for this video. I hope it helps you to understand clock skew and clock jitter and their effect on setup and hold timing constraints.